There were no real surprises on that test, I would hope. We're going to start the new chapter now. It's going to be the first real chemistry we're going to do. All right? If you think about it, up till now, we've been doing a lot of preliminary stuff. So get your notes out. And I'm going to give you the first of the real chemistry chapters. We're going to start talking about atoms, atomic structure. Now, you'll have seen most of this stuff before. All right? You'll know about, the stuff we're going to talk about, protons, neutrons, electrons. You'll have seen a lot of this stuff before, the periodic table. You've even seen that before a little bit. But we're going to go into a lot more depth in all of these, okay? And we're going to start with a little bit of history. Now, I do not do a lot of history. I do not do a lot of... I forgot my bucket. I gave it... It's in Trader's.
Why? Can I go through that?
No, go. I don't do a lot of, scientists' names and stuff like that. And there aren't a whole lot of scientists you need to know. But the ones that I'm going to give you today are those few that you will. Pretty famous guys and pretty important in the atomic theory. Every now and then I'll give you, there's a few scientists as we go along. Besides this chapter, the guy who came up with the periodic table, we'll talk about him, and a few others. If you think about biology, what scientists do you remember in biology? Not many, but who do you remember? There's a couple. Mendel, he was he did a lot of the work with those pea pods and genetics, right? What else? Who else? Obviously a big one in evolution. Darwin, okay? So there's a couple of scientists you know in biology, and they're kind of like common names. These are the guys you're going to need to know for atomic theory, and there's a few others throughout the year. Probably you can count them on maybe one hand, maybe two hands at the most, the number of scientists are going to get you. I'm not going to ask you to memorize dates, although the dates are going to be up here. It's just about what they did and the process of how we got to the atomic theory. Because this is the crazy thing. You can't see an atom. And, when they came up with these theories of atomic theory, no one could see it. You'd be surprised how far back it goes, too. All right, let's start with Chapter 4. It's actually skipping around a little bit. You might say, well, what happened to Chapter 3? Well, we kind of skip around a little bit. Sometimes I mash stuff together from one chapter to another. If you look in your notes, if you look in your book, most of the homework's going to come out of Chapter 4 this time. Okay? And that's on atomic structure. All right, let's start with a little bit of history. Okay, a little bit of history. First guy to come up with the atomic theory was a guy called Democritus. And you might be surprised to find most of us think of the atomic age, the atomic theory, probably, as something that, maybe you think of Einstein. There's a couple of famous scientists you can think of. Maybe you think of Einstein. Maybe you think of certainly the 20th century you would think of. But you'd be surprised to find that Democritus lived areas. He's a scary guy, too. Look at this guy. I would not want to mess with him. He's like a scoundrel. He's mean. He lived around 460 to 370 BC. It's like 2,500 years ago, practically. Okay? 2,400 years ago. 2,000 some years ago. The first guy that came up with the idea that there could be this small, indivisible particle called atoms. That's what he came up with. You say, well, that may surprise. I would think that should surprise you because that was a long time ago. But it shouldn't surprise you too much. We kind of have this, I don't know what the word is, arrogance about our own day and age. You guys think you're so much smarter than you are. All right? You really think you're the most intelligent generation that ever lived. And you have that idea, we'll talk about Darwin a second ago, from Darwin. Evolution has created, you are the perfection of the species right now. Well, that's a joke. All right? And you're absolutely wrong about that. All right? 2,000 years ago, people were smarter than you. A lot of people were smarter than you. What do you mean? They thought the earth was flat, and they thought all these stupid things. They believed in spirits and tree spirits and druids and all this other stuff and alchemy. And we all know that's nonsense now. Yeah, but you guys think you're intelligent. You can't think for the most part. Your language skills. For example, a college student graduating today doesn't even have to take a language for the most part. Okay? To be a college student, to be graduated from college back in, just 100 years ago, in the early part of the 20th century. I mean, you had to have all spoken and be able to, read and be able to translate Latin and Greek. Everybody did. And it didn't matter what your major was. And you had to be able to, be able to think logically, and you had to take classes in philosophy. And nowadays, you can go through your entire college career and never take a class in Shakespeare. You never really read anything except your own one little specific major. You're not really that much more intelligent than people who lived before you. You think because you can look it up at Google, that makes you smart. Because I have my cell phone, I can look something up. It makes me intelligent. It doesn't. It makes you absolutely no more intelligent than people who lived 1,000 years ago. Evolution doesn't work that way. You don't get smarter over time. The human species doesn't just get smarter over time. A lot of times you guys think that. A lot of smart people lived before you, and we kind of feel like we're so much smarter than them because they thought the Earth was flat, and they had all these dumb ideas. But honestly, your vocabulary, by almost any measure, your vocabulary, how many words you know, how you can speak, how many languages you can speak, your knowledge of philosophy and logic and everything else, by almost every measurement, not every other, every measurement, you're not as smart as them. I'm not as smart as them. I graduated from college, obviously a while ago, and I always felt inadequate because if you look at the way what people learned, just hundreds of years ago. Now the difference is we put way more people through college now. Way more people go to college than ever did. So as a whole, I suppose our society is smart. I mean, there were people who worked on the farms and slaves. That's what you had hundreds of years ago. They had no education at all, couldn't read or write. Now we educate a lot more people to a minimal degree. But when you graduate from high school, you will not be as smart as your great-grandparents who graduated from high school. And the difference is, many of your great-grandparents didn't graduate from high school. My grandfather graduated from 6th grade. My father didn't graduate from high school. He went to the service and he eventually got his GED. Most of your great-grandparents didn't graduate from high school. But if they did, I will guarantee you they had a better education than you do. Because we spend so much more time teaching you to be tolerant and sex ed and all these other nonsensical things that, kids just watch the farm animals and they learn sex ed. That's all they had to do. They didn't have to go to class for that nonsense, and all the other stuff that we do in class, in school nowadays. They actually got an education, whereas you don't. So I always bring this first guy up to show you that you're not as smart as you think you are, and people who lived a long time ago, they're pretty smart guys. Aristotle, Plato, these weren't idiots. Okay, he was the first guy to come up with the idea that all matter is composed of indivisible particles. Now there is a problem with these guys that lived back then. They had no real reason to believe it. They had no evidence for it. Okay, so we'll talk about that and why. I wanted to show you this. The idea for the atomic theory, the word atom is a Greek word. It comes from, it means indivisible particle, small indivisible particle. All right? The idea came a long time ago. However, we didn't have a whole lot of proof for any of this stuff. We didn't have a whole lot of evidence for any of these theories way back when. Aristotle had his own theories about science. He wrote about science. Okay, Plato. These guys all had ideas about science. But they didn't really run experiments like we did. They didn't really use a scientific method. They kind of thought about things. They observed things, and they made conclusions based on logic. And sometimes they were right, like he was right. All right? All things are composed of atoms. But sometimes they were way off, too. So I wanted to go through the process here. You got guys that come up with the idea a long time ago, but no real evidence for it. It took a long time. So you get a guy by the name of Dalton, who, and we're going to talk about him again when we get to gas laws, who finally came up with some evidence for the atomic theory. Okay, and he looks a lot smarter. Look at him hold his finger up there. Very smart guy. All right, he lived but still a long time ago. And we're not talking Einstein here. We're not talking the atomic bomb. We're talking 1800. That's over. Well over 200 years ago. Okay? Wait. What's today's date? 2014? How many years ago was that? It is over 200, right? Yeah, it's over 200. Oh, just making sure it's well over. Not well over, but it's over 200. Okay. So, yeah, again, it was over 200 years ago that we first get our evidence. Okay? And here's what Dalton said. He actually had 5 statements that he came up with, the atomic theory. What we still kind of talk about today is the atomic theory. However, there are some problems with his statements, okay? There are some problems. I want you, instead of wasting my time having you write all these down, I want you to just write underneath here, see the sheet, because I'm going to give you a sheet in a little bit that's going to have those statements on it, as well as some of the pictures and the graphs graphics that I'm going to show you out here, okay? I don't want to waste time writing all 5 statements down, okay? So just write C sheet, and so you know to look there. All right, let's look what he said, so we can just pay attention instead of writing. All the elements are made of atoms. That's good, but you know what? Democritus said that 2,000 years before him, over 2,000 years before him. So he can't be famous for just saying something that a guy said 2,000 years before him. He can't be famous for that. He said atoms cannot be subdivided. Is that correct? Are there anything smaller than atoms? Are there things that are sure? We already know about protons, neutrons, and electrons. It turns out there's other things, quarks and hadrons and leptons and all these other crazy things too that you don't even know about, and I'm not even going to talk about with you in chemistry. So he was wrong on that one. How about this guy? All atoms of a given element are identical. Was he right about that? Are every single carbon atom and every single oxygen atom the same? No. Turns out we have different isotopes. A different isotope of the same atom. Hydrogen has 3 isotopes. Protium, deuterium, tritium. He was wrong again. This guy's an idiot. He didn't do anything right. He took somebody else's statement, and the other 2 things he said are wrong, and we know them to be wrong now. So why are we talking about Dalton? Well, here's the thing. He wasn't an idiot. He basically, these 2 things, at the time, we didn't know this. It was incorrect. But the big thing he's famous for is actually doing experiments and having a way of some reason to believe that there was a small indivisible particle. Okay? He did some experiments, and he realized that if I take elements, they always combine in a whole number ratio. Like, for example, water. What is water made of?
Hydrogen.
Hydrogen oxygen. But what is the ratio of it? It's going to be 2 to 1. And he realized that carbon monoxide or carbon dioxide. You can have 2 different kinds of carbon and oxygen together, but it's always a whole number ratio. You realize that? Geez, that must mean something. That means if I break it down to the smallest and smallest level, there must be a point where there's something, we'll call it an atom, combining, some one individual thing combining with 2 individual things. Because it always, when he weighed them, found out they were combining in whole number ratios. Okay? And he also believed that that's what was happening. When you put these guys, he would do experiments, and he'd put these guys together, and he would be rearranging these atoms, and you'd always get the same number on both sides, and you'd always get a whole number ratio. So he proposed, based on that experiment, he proposed some evidence for the atomic theory. And that's why he's really famous. Now, after Dalton, things kind of take off. It took 2,000 years to get some evidence for the atomic theory. Things kind of take off after that. He's important. And again, you can write this down. You can leave the space here. You don't have to write it down. You can write this statement down. He's important because he based his theories on quantitative measurements of chemical reactions. He didn't just come up with a theory like Aristotle or Democritus and, use logic to figure out stuff. He actually did experiments. And that experiment supported the evidence supported the fact that there must be individual small particles. Now, since then, we have found, of course, that there are smaller things in atoms. All right? And the first guy to come up with that was a guy by the name of Thomson. And here is a picture of him. And by the way, I even have these pictures here, so but you can write these notes down. You're not this long. Thomson, see. I even have these pictures on the sheet I'm going to give you. Now, Thomson did some experiments, and he found some stuff out about. I think I've got the video that's going to come up here first. Let me see. He worked around 1897. Notice that's within 100 years of Dalton's work. Okay, so things kind of take off. It took 2,000 years to get any evidence. Now we're starting to get some stuff with even smaller things than atoms. Hit that light for me. I think this should be the video next, yeah.
To demonstrate a Crookes tube, a cathode ray tube, we need a high voltage power source, such as this one. We need the Crookes tube, which has a metal cathode, a metal anode, a screen that has been coated with a phosphorescent material that gives off light when struck by electrons, and a bar magnet.
Now, I used to have this exact same device, but one year, not too long ago, about 5 or 6 years ago, I came back in the summer, after the summer, and it was in pieces. It must have fallen off. It was up, used to be up on my shelf up there, and it must have fallen off. From whatever the custodian's cleaning up or whatever. So it was just in pieces. I used to be able to show you this. And I've been only able to find these things since then in any catalog. I think part of the reason why is that when you hook this guy up, there are at least some of these guys. Actually, when you pass a high voltage through some of these things, I think Schrader has one over in his room. It actually can give off X-rays. It's kind of dangerous. You shouldn't really show it to you anyway. But what it is just a tube, a glass tube with all the air sucked out of it. Okay, all the air is sucked out of it, pretty much all the air is sucked, and there's a fluorescent tube inside of it. And you're going to hook up a power source to it, positive and negative, and pass electricity through it. Watch it. Watch what happens.
We turn on the screen. We notice that the electrons are emitted from the cathode, and as they strike the fluorescent screen, we're able to see the cathode ray, this stream of electrons illuminated. We can use a magnet to show the deflection of that stream.
Here we can see the electrons being deflected by the magnet. The cathode ray moves upward.
Which side do you think the magnet's there? If it's moving upward, what charge do electrons have?
Deflected in the opposite direction.
Negative.
And we observe that the beam is deflected downward.
By the positive side. Okay. So what basically Thomson discovered were electrons. Got light back on for him? All right. He discovered negatively charged particles called electrons through his experiments. And what he made, what that thing's called a cathode ray tube, or a crux tube. I want to add that on. I don't have that actually. I really can use that word. Using a cathode ray tube. That's kind of a famous one. Famous experiment. Cathode ray tube. Also, you're going to see the word cathode in the future when we talk about electricity, chemical, electrochemistry. Okay. All right. All right. So that was Thomson. It took 100
a crux.
This is another picture. I think that's the one that's in your book. Now, Rutherford.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
Now, basically, he was firing alpha particles, which are positively charged, at this stuff. And he found that sometimes they deflected, which means that there's something in the nucleus that's probably positively charged, too. What are those things that probably deflected those alpha particles? What do we call them? Protons. Positively charged protons. Remember? Here's basically what he did. And this is the picture that's in your book as well. All right? He took a very thin piece of gold foil. So thin it was basically transparent. You could see through it. That's how thin the gold was. Transparent. And he fired particles at it. Now, they found that 90% of these particles just went straight through the gold foil. They didn't do anything. All right? But a few of them were deflected. Now, that tells me two things. The ones that were deflected tells me clearly that they must be hitting something positively charged, it's being reflected, being deflected, and therefore we've discovered protons in a nucleus. But there's something else you discovered as well I want to talk about after you write that down. the fact that most of them went straight through tells me that most of an atom has what there? What is there in most of an atom? Nothing. Space. Electrons are flying around, as you guys already know. Let me show you what I mean. How much. That picture you saw a little while ago is by no means to scale. Let me show you why. All right. Here's an atom. So let's just say this is the size of an atom. Okay. If the atom were as big as a soccer field, okay, so here's your soccer field. If the atom were as big as a soccer field, okay, goals here, goals there. The size of the nucleus, where those protons and neutrons are, will be the size of a pea, an actual pea, okay? That's how much of the atom is empty space. So what it shows, this picture, there's no way to show it representative on a picture like they were showing you a minute ago with these particles going through. Because remember, this is the size of a soccer field. And there's a P in the center. The rest of it is just empty space filled up by these electrons that are moving around in orbitals. All right? So the second thing that Rutherford figured out, not just that he discovered positively charged particles called protons, but most of the volume of an atom is just empty space. Kind of like the theory behind Honey, I Shrunk the Kids. Remember that? Ever seen the movie? Yeah. I mean, that's actually what they talk about in the movie. You can't really get rid of that space and shrink it down, but that's the theory behind it. He was right when Rick Moranis talks about most of an atom being empty space in that movie and then shrinking things down. He's right. Most of an atom is empty space. I don't think you can shrink people down and walk in the grass and fight grasshoppers and stuff or whatever, but still, I guess it's possible. All right. So, again, I'm just trying to show you a progression of what's going on here. You got Democritus, thousands of years ago, come up with the idea of the atomic theory. Dalton comes up with some evidence for the atomic theory. Thomson and Rutherford, they expand on that and even find things smaller than the atom, electrons and protons. Okay? And again, this is not by any means to scale. If this were to scale, that's about the size of a pea. This atom should be the size of, like, not just this room, but the whole building, pretty much. All right? And that's why most of the atom is empty space. Most of those things went straight through. Okay. Now, it's hard to believe, but this is kind of a crazy thing. We're going to talk about Millikan here. It seems like if you can't really see, and no one can see an electron. You can't really see an electron. A lot of times you guys think, when we talk about these particles, we just get a really big microscope and we can see a proton, we can see a neutron, we can see an electron, and we can see all these things. Okay? And then the things that make up those things, even, we can see them. But it's not really true. All right? They're so small, and in the case of electrons, they're moving so fast. All right? There's not really any way I can measure them accurately. All right? So how do we know anything about them? How do we know, for example, I'm going to tell you as the year goes on, you're going to know the mass of an electron, you're going to know the charge on an electron. Okay, you're going to be able to know all this stuff. How could you possibly know it if they're that small? Well, it's kind of like this. Look at this. If I gave you this ruler, and I told you to measure the thickness of a piece of paper, how thick it is, not how big it is, but not area, but how thick it is, with this ruler, you say, I can't do it. Can I do it? What could I do to measure the thickness of this paper? Accurately. Very accurately, actually. What could I do? What do you think I could do? Yeah, I can measure the whole thing and then divide by how many pages I have, can I? See, that's called indirect measurement. And much of what I'm going to tell you about atoms is gotten that way. It's not gotten by picking up an atom and putting it on a scale and telling you that's his mass. You can't do that, all right? But by indirect measurements, okay? And by indirect measurements, Millikan was able to determine, well, what?
In 1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet.
When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of a smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.
Okay. All right, so you see that's a indirect measurement. He wasn't able to pick up an electron and put it on the scale or measure the charge on an electron. He was able to measure large amounts as they fell, well, large being a very fine, thin oil, and adjusting the voltage and seeing where that voltage had to be, and then taking the multiple of that. Like when I say multiple, kind of like this. Can I tell, like, bowling balls come in different weights? Anybody in the bowling team? All right, excellent. Next is the point. All right. Let's say we shipped cases of bowling balls, okay? All right, I can actually, I know how many bowling balls are in each one, all right? And I can figure out, if I weigh the different cases, all right, I can tell how many are in each case. I could probably figure out what the mass of each bowling ball is. Because it would be, here's one that's half full, here's one that's full, here's one that, it would always be a multiple of some number. That would be the small, say it's a 9-pound ball. It would always be the multiple of that number. And that's how he was able to do that, okay? So he worked around 1909, just right after Rutherford. Sounds like I'm listening, Rutherford. Rutherford? Sounds like I'm listening. He worked right after Rutherford, and he determined the charge on an electron. So not only do we know about the existence of these particles from Thomson and Dalton and Rutherford, but we now know we can even tell the charge on an electron. All right, by indirect measurement, doing these kind of things. And again, I've got these pictures also on that paper I'm going to give you in a little bit. Okay. So what Millikan did, he determined the charge of an electron, suspended a charged oil droplet using electrodes. And just like if I were to, like I said, weigh multiple boxes of bowling balls that are coming in, all right, if they're all 9-pound balls, I'll be able to tell that because every box I weigh will be even though I don't see an individual bowling ball, I'll be able to tell every box I weigh fill different amounts, half full, third full, quarter full. I can tell there'll always be some multiple of whatever that ball is in there, whether it's a 10-pound ball or a 9-pound ball or a 12-pound ball. Okay, so he determined the charge required to suspend the droplets were all multiples of a charge, 1.6 up to the 19th coulombs, and that must be the charge, I should say, of an actual electron. It's kind of crazy, but that's how you do things. When you can't see them, you have to make indirect measurements.
What makes one atom?
Sorry. There we go. We got the copy?
No, that's it.
All right. Well, we aren't going to be able to finish, but we're going to start a little Bill Nye video, a little clip on atoms today. Okay.
Are you certain?
Of course.
You found them in everything.
Yes, sir. They're tiny, they're filled with empty space, and they are the fundamental building blocks of all matter.
So, If we could somehow control the market on these things, just think of the possibilities.
Sir, you're talking about
Remember Bill Nye?